These series of videos are demonstrating how to automate economic policy through code. A link to the GitHub repository is included in the video description. In the previous video, the problem the System Accounting app solves was presented. In this one, we'll eliminate the mystery of the equation and dispel a myth. Then, in the next, begin demos and code reviews. What is this? This equation features the Greek letter sigma. We'll look it up. Sigma, when used in math, describes a sequence of numbers, then adds them up, which is useful if you want to add more than two numbers. At the bottom, you say where you want your sequence to begin, and then at the top, you say where you want it to end. The person who wrote this sigma wanted the sequence to start at 0 and then end at 5. And with nothing fancy happening here with the k, you simply increment by 1, from start to end. 0, 1, 2, 3, 4, 5 is the sequence, and then adding them up gives you 15. That's it. That's sigma in math. So which sequence are we adding up here? U refers to the number of transactions happening in a single second. I refers to the number we begin counting them from. In this case, we begin counting transactions from 1. Then W, borrowing the rest of the numbers from the previous example, is just the amount per transaction. Beginning from 1, going to 5, then adding, gives you a GDP per second of 15. What's most important, though, is what's happening here in the W. W measures the value conserved per transaction. This word conserved refers to a property in physics people are accustomed to only describing a type of number. In system accounting, a law of conservation is now extended from numbers to string values, which is the data type for ownership. Spoiler alert. If you lend your money to a finance company in system accounting, applying a physical law of the universe to money protects you from being told they still have it after spending it. No one will be exercising the right to supply you fiction because they have a license from a government claiming the supremacy of a democratic mandate. 3 men don't make a tiger or a credit. All right, let's move to an example suited for accountants. Beginning with the definition that a number is conserved if it doesn't change under transport, John visits a grocery store and purchases a loaf of bread for 5. John's account goes down by 5. The store account goes up by 5. The number 5 is conserved when it doesn't change after moving between old and new owners. You can see motion appearing as string values serve as coordinates, so let's move to an example suited for physicists. We're gonna get abstract for a few minutes, but we'll flesh it out with some context after. And if it still doesn't stick, no problem. Don't need to scale walls when you can click buttons. Useful software automates away the learning curve. In system accounting, double entry accounting is performed by recording transactions as dual complex numbers. These two-dimensional objects help describe motion in a 3D space. Transactions are small, instantaneous events that describe how goods and services move between old and new owners. That is, in a space having volume. We'll skip adding values to this table for a moment and just talk about the columns. Starting from left to right, the first column lists real numbers, or the price of a transaction. The remaining 3 columns list numbers that enable us to describe movement in 3 dimensions. Then the last 2 columns, with the E-looking epsilons, also require their numbers to square to 0. So they behave like the second column, but they also square to 0. And when they do, our 3 dimensions collapse to 2. Now every time one of these numbers are added to the database, they're just describing small slices of movement in 3 dimensions. Okay, let's add data. The story is, John brings a loaf of bread to the store counter. The store owner asks 5, John bids 5. And in finance, when bid equals ask, we have a transaction. The real number is 5. The values in the remaining 3 columns describe the instantaneous motion across volumetric dimensions, which is fancy talk for a space containing goods and services and the people who trade them. These account names are different from one another. That is, to humans, they're not identical. But to the universe, they just form a point where -5 and +5 meet. Prices are used to tie 2 accounts to the same number. When creating projective lines, think about money traveling between old and new owners in a straight line. You need coordinates for that, and not just any, but homogeneous coordinates. Adding a dimension where accounts are tied to the price they're agreeing to gives us the ability to draw a line through the transactions, or collineate them. Now, as said before, these numbers we're using in the remaining columns help us describe movement in 3 dimensions. But what wasn't said before was the shape of the movement, or how does it look when you're moving. We're not using integers here because these dimensions were repurposed to store string values assigned to numbers so they can behave like numbers having positive and negative orientation, but whenever one of the events structured and stored by these records appear in the database, you are observing a rotation. Now, this is a database receiving records and behavior is binary. So observing a geometric rotation from beginning to end is replaced by an algebraic rotation. We're only interested in modeling these events for the sake of a sign flip, and passing in an accountant's T-account entries where duals expect to square to 0 identifies where the axis of rotation is located. For the buyer, or debitor, this single record completes half of a sign rotation that began in the past. That is, the buyer earned 5 in the past and is spending it now in the future. And that is the rule. To debit in the future, you credit in the past. The seller's half is only beginning a sign rotation they will complete in the future, when they purchase something. That is, the store owner is currently earning 5 and will spend it in the future. So a transaction with this structure says, whatever the seller buys in the future, when they debit, is a reflection of what they sold in the past, when they credited. Together, these values are recording sign rotations across accounts and the goods and services they trade. The account names, joined by price, are angle-preserving coordinates. Their role changes in the transaction, that is going from creditor to debitor and vice versa, describe the orientation of the projective line passing through those coordinates. So dual complex numbers help model instantaneous rotations and reflections, enabling buyers and sellers to sign flip their way through 3 dimensions or volume without violating a conservation law. Alright, now we'll flesh it out. With ownership receiving a dimension through which value flows and behaves as an angle-preserving coordinate, think of every second, with all the transactions happening inside of it, as a single frame in a film strip. And each frame, one following the other in this film, as protecting continuity across all the others. The left side, it's art. A new symbol authored by someone saying you're entitled to an economy that gives you a full view of the economic game board. If you visit combinatorial game theory, you'll see these 2 gentlemen playing a board game. What's important is that both can see the entire game board while competing. The current economy does not supply people this power. You could end up paying a few thousand more for a car than if you bought it down the street. Of course, the dealer's not going to tell you that. Or you could end up casting a vote for someone with dozens of fiscal skeletons in their closet and never be the wiser. Then there's Wall Street. And unequal access to information is its honeypot. For example, if you run what is called an investment bank in New York, you may know of the operating costs belonging to a firm valued at $500 million. Then you discover another larger firm with similar equipment that operates at half the cost. So you create a slide deck and spreadsheet otherwise known as a pitch book, and then advise the larger firm to buy this smaller firm so they can exploit doubling the smaller firm's profit with equipment the larger firm is operating at half cost. The investment bank fee for this advice is 5% of the purchase, which is $25 million. Maybe the investment bank folks spent $1 million of their own money to complete the deal. Their profit margin is 96%. That's not an efficient economy. You'll have to work a lot harder than PitchBook to earn $25 million after spending $1 million in an efficient economy. With system accounting, some gamer would figure all this out from their basement in seconds, for free, and propose an optimization with a transaction automation rule, charging a lot less than 5%. So no $1 million to enter, or requiring then exploiting dinner party access to the folks at both firms. Alright, left and right hand side mystery solved, now the myth. Is this a cryptocurrency? No. Silicon Valley snake oil aside, encryption is applicable, but you don't have to call its application a transaction data cryptocurrency. Is this a blockchain? No. And please use the word replication. Just insist someone explain how records are replicated. If they tell you it's happening more than a few times for high availability and consistency, they're selling an overly designed, wasteful, and latency-filled replication scheme. Encryption and replication are not relevant to the data structure that models currency as a current, or solving economic issues by replacing monetary policy with the natural physical law. Okay, that's the mystery and the myth. In the next video, we'll start demoing the solution and reviewing some code. You may subscribe, share, and contribute from the buttons and links in the description.